Okay, hello and welcome everyone. So this video is going to be a solution walkthrough to the second exam in economics of entrepreneurship. And so it's basically thinking about what is it that we can gain from applying intermediate microeconomics to the idea of launching a new business or exploring a new industry or something along those lines. So that's the idea. What I'll do, same as all my solution walkthroughs, is I'll show the exam first. So you can stop the video, think about the questions, and then I'll give my solution. So beyond these true-false conceptual questions, there's questions thinking about quadratic network, so quadratic network demand, thinking about bargaining, where you're solving by backward induction to think about a bargaining situation. There's a Stackelberg oligopoly question. There is a incentive contracts question. And what did I miss? There is a repeated prisoner's dilemma, tacit collusion question. Okay, so I guess sorry, I probably could have just, like, as I'm giving my explanation, I probably could have been like paging through the exam. So sorry about that. All right, a couple more questions and then I'll be able to go through the solution. Couple more from this point, right? All right, so here was the Stackelberg question, and then here was the incentive contract question. This one here actually was just the exact same one from the lecture, but I changed the outside option to 80,000. So. All right. Oop, sorry. The version that I've got is gonna, with the solution, is going to be my handwritten solution. I originally wrote this with marker, so I may need to interpret some of these for us, or like help clarify some of my writing in a few places. Anyway, so for the true and false with brief explanation, I was looking for the designation of true or false, and then a 1 to 2 sentence explanation that reinforced your reasoning. That way, like if you had the true or false part incorrect, but your explanation was correct, maybe you could get partial credit. And also then, requires you to have a better reflection than what could happen from just like quick true or false, just guessing or whatever. Right, so anyway, so well, what I'll do is I'll read over the question and then give a couple of thoughts, but really I was looking for what would reinforce, like there's maybe you'd have an example from lecture or just remember true by definition or whatever you wrote. So as long as it reinforced and made sense in the context of what we were looking for here. All right, so VC typically fund larger investments than angel investors. They tend to finance projects that will cash out more quickly. True, yeah, they're looking for a high rate of return and they want kind of a clearly defined plan for how they're going to get their funds out. So they want to know what the exit's going to look like. And they want to be sooner than angel investor, which might be not necessarily, but a little bit more hobby related. Okay, so next one. In a sole proprietorship, owners are insulated from debts of the firm. That's false. I mean, with a sole proprietorship, remember one of the things was there was no separation between the owner and the business. And so the owner wasn't separated from the debts of the firm. The owner is responsible for the debts of the firm because they're viewed, at least in the eyes of the law, as the same entity. All right, so bank loans are a good source of funds for an entrepreneur whose primary expenses are investing in equipment that can be sold off at a minor loss, investing in an established franchise, etc. Yeah, if you can sell something off at a minor loss, the example from class was like, if you want to start a mobile vet business, I think was one of the ones that I had, right? Or mobile personal trainer. You're going to buy the van, you're going to buy the equipment, and maybe have a loan for those, and business fails or decide you don't want to do it anymore, whatever, you can at least sell those things off. There's something that stands as collateral. You might also categorize an established franchise in that same category, thinking about something along the lines of like, a McDonald's or, something with a pretty strong established franchise name, Starbucks or whatever. All right, so true false with brief explanations, 2 remaining. So suppose you're negotiating with a dealer over a car you'd like to buy. You're in a worse negotiating position if the dealer has a high patience level and high reservation value. Higher patience, right, closer to 1 meant that the future value would be discounted less, or that you could carry whatever was the surplus that you were going to get, into the future. So if we said patience is a virtue if you're interested in getting a better deal. So, if the dealer has a high patience level, that's bad for the buyer. And if the dealer has a high reservation price, that's bad for the buyer because that's going to be a higher required sale price. All right, so if you're operating a platform market, you seek to relatively subsidize the group that most benefits the other group, creating additional incentive for those high-value customers to join. Yeah, so if you have a platform, thinking about something like social media company or whatever, where you've got a collection of users, you'd relatively subsidize their use of the platform. Maybe you'd offer it'd be free, probably at least initially, to generate a really large network, and then the reason why you do that is they most benefit the other group, which would be the advertisers. So you create an incentive for the high value customers to join. From the perspective of the platform, the high value customers are going to be the advertisers who are going to be, buying space on your platform to display their ad copy. All right, so now the quantitative ones. Consider a network good where there's 300 million customers with their individual valuations uniformly distributed from 1 to 100. Their overall willingness to pay given by their valuation times the number in the network, V times N. And the industry involves constant cost given by average total cost equals marginal cost, which is equal to 4,800. All right, so the way we did this, as I said, first remember we'd want to just start off by thinking about what would just the demand for the product look like if we had to fit all these individuals onto the demand curve. Right, so the starting place I always think of is, we've got individual valuations uniformly distributed from 1 to 100. Somebody's willingness to pay is 100, somebody's is 1. We think of the vertical intercept of the demand curve as corresponding to willingness to pay, right? The height of the demand curve corresponds to the marginal benefit to the consumer, so this is going to be 100. Sorry, it kind of got cut off there, but this would be like 100. And then what's going to be the horizontal intercept? Well, that's like the size of the market, and we've got to fit 300 customers onto this demand curve. So if this is 100, this is 300, that means this thing has to have a slope of 1/3. So my inverse demand is going to be prices equal to 100 minus 1/3 N. And then using this expression, we're going to realize that the overall valuation is going to be whatever is their idiosyncratic valuation for the item itself, scaled by the number of people that are in the network. So that's why we'll multiply that thing by the number of people in the network, this N. And this is just following what we did in the slides. This was this was lecture 9B, lecture 9B, network externalities. And I can't remember for the playlist on YouTube if I put those in the same lecture or not, or if they're standalones, but whatever. All right, so we've got our expression. We're going to set this equal to 4,800. Right? So we've got basically our demand on the left, our supply on the right, and we're trying to find equilibria, right? We're trying to find these equilibria. This is the demand curve. It's going to be a quadratic. Here's the supply curve, cost curve, right? So it's giving us the role of supply. Like formally, a firm with market power doesn't have a supply curve, but it's basically what it's doing is it's representing the production costs. Okay, anyway, so we've got this nice quadratic. You could factor it, right? You could probably factor by grouping maybe, or you maybe kind of look at it, remember all the factoring techniques from like high school algebra or college algebra or whatever. I don't know. For me, it's just easier. Just use the quadratic formula. Quadratic formula is going to give you the zeros of this polynomial. It's going to be like, when is this thing equal to 0, right? Quadratic formula is minus b plus or minus the square root of b squared minus 4ac. That whole thing divided by 2a, right? And so the b term, okay, sorry. So this is the a term, 1/3. This is the b term, right? Minus 100. This is the c term, 4,800. So we're just going to plug those things in. It's going to be 100 because it would have been minus 100, but it's negative b, so that becomes positive 100. Plus or minus 10,000 minus 6,400, right? This becomes 6,400 because that was 4 times 4,800 times 1/3, right? And so then 10,000 minus 6,400 is 3,600. The square root of 3,600 is 60. So it's going to be 100 plus or minus 60, basically, times 1.5. Because 100 plus or minus 60 divided by 2/3, when you divide by a fraction, it's the same as multiplying by the reciprocal. So 2 divided by 3 is 0.66667. Well, I didn't give enough sixes there, but you get the idea. When you multiply by the reciprocal, it's a lot cleaner. It's just 1.5. And so it's going to be 160 times 1.5, which will bring us to 240, or 40 times 1.5, which brings us to 60. So the possible network sizes, this would be the large stable network, this would be the small unstable network, and then the zero network is always possible. So we said of our network equilibrium, or of our equilibria for our quadratic network demand, we have two that are stable, 0, and then 240, and then one that is unstable, 60. It's unstable because if we compare the marginal benefit to the marginal cost, the marginal benefit represented by the demand curve, to places between 0 and 60, the marginal benefit, the demand curve, is below the marginal cost. So if the marginal cost is greater than the marginal benefit of joining the network, you'd actually not want to join. People would leave, and so then it would shrink down to 0. Between 60 and 240, the marginal benefit, the demand curve, is higher than the marginal cost. So the next consumer to join definitely will. And so we keep increasing the size of the network up to 240, but 240 would be the largest sustainable size of the network. Beyond 240, this would be like maybe we'd sign people up, but they would quit, they'd leave, because their marginal benefit is below the marginal cost. Okay, so that's relevant for part B and part C. If 50 million signed up, well, that's less than 60. So those 50 people are going to leave the network, right? So maybe that's like Google Plus, right? Google Plus tried to rival Facebook, and now there's no Google Plus, right? 100 million sign up. What happens to the network size? Oh, now it gets to the really big equilibrium, right? Because 100 is bigger than 60. So those 100 people stay in the network, but then the 101st person also wants to join, and so on up to 240. All right, so for bargaining, now we're negotiating over 30 ounces of ice cream. Explain your logic where. Firstly, you have a full bowl of ice cream, then we have 2/3 of bowl, then we have 1/3, following this offer pattern. Person A is going to make an offer, B could accept or reject. If it's rejected, B makes an offer, but now only has 2/3 of the bowl of ice cream to make the offer over. A accepts or rejects. Then if A rejects, A then gets to turn around and make the last offer. B accepts or rejects. And it's basically an ultimatum game in this last period. So I chose nice numbers for you because you could either do this in 30, 20, 10, or 2/3, 1/3, right? Same thing down here, 5, 6, 1/3, or 30, 25, 10 would be the size of how much ice cream is remaining. This is corresponding to, maybe you've got a hypothetically profitable entrepreneurial opportunity coming up over the summer, but you need to have your equipment. Maybe you're going to rent some equipment for whatever you're going to be doing over the summer, but you want to make sure that you've got that pinned down before the summer arrives, because you'll lose customers to prospective rivals or something. So the possibility of earning profits, whatever those profits are, diminish over time. As the longer it takes to come to an agreement, the worse it is, and then maybe it's not worth even doing at a certain point if the summer's over or whatever. Anyway, so how does this work? Well, we go to the last period, and we say in the last period there's going to be 10 ounces remaining. Person A is going to make the offer of 10-0. B will accept because we'll say B is going to be indifferent between getting 0 from the offer or getting 0 from rejecting. So A is going to guarantee themselves 10, which means when B is making the offer, B, if we can figure this out, B can figure out that A is counting on getting at least 10. So of the 20 remaining, 10 has to go to A, and then B proposes keeping 10 for themselves. Well, if that's going to happen in round 2, then we know that if we can figure out that B is banking on being able to guarantee themselves 10, A can anticipate this as well. So then when A is making its offer initially, A is going to offer that 10 to person B and only 20 for themselves. And then looking forward, reasoning forward, each can figure out what's going to happen. And they're like, well, wait a second, we could either negotiate down and then A gets the 10 they're going to get, or we could accept immediately and then A gets 20, B gets 10, which is all they could ever expect, where they get an accepted offer in round 2. So the distribution then would be 20-10 or 2/3, 1/3, right? And we'd expect that they're going to come to agreement immediately. Same thing down here. So now something different happens here. Now there's 10 remaining in the last period. For the same reason, I think maybe I reverse these right here. Sorry. So for the same reason, A is going to be able to get all 10 in the last period, right? So then, oh no, I didn't. It's late. I'm confusing myself. So A is going to get 10 for sure. So B has to offer 10 to, maybe I was confusing myself up here, whatever. So person A is going to get 10. There's the 10 that they're going to get in the second round. B is going to therefore be able to keep 15 out of the 25, because if they fail to come to an agreement here, and maybe A would, A realizes that they're going to get 10 in the last round, right? So B has to offer A at least 10, and then they can offer themselves, propose keeping themselves 15. Looking forward, A knows that 15's counting. Looking forward, A knows that B is counting on at least 15 in this round. And so A has to offer B at least 15, could keep 15 for themselves. That's a 50-50 split. So 15-15 or 1/2, 1/2, right? Okay, so then my question was, do any of these yield a split where they get 50%? Yeah, they do. So part B does. In what scenario does person B prefer? Also, person B prefers scenario 2, because person B gets 15 there instead of 10. And what's going on here is it happens that this non-constant decay rate, right, tips things in favor of person B and tips things away from person A, despite the fact that we have an odd number of periods, right? Remember, if you have an odd number of periods, as the number of periods extends to infinity, we approach the 50-50 split, in the limit. Also, if you have a weird discount thing, like maybe there's something happening where, time, the time elapsing during this negotiation over maybe this first week might be far less valuable than the time elapsing in the negotiation over the second week or third week or something like that, right? So maybe not much is happening. If we're thinking about period 1 is negotiating over the winter, and then all of a sudden period 2 is negotiating once the snow melts and now it's spring. All of a sudden, well, wait a second, we're really losing out value. Time is way more expensive now than it was previously, might be the story. Okay, so the following payoff matrix depicts the outcomes that result when two businesses interact in a strategic game. Each has two strategies, high and low, referring to the prospective pricing strategy each would use. The payoffs in the matrix reflect the profits to each for a pair of strategies. Within each cell, first number goes to row player, second number goes to column player, right? So row strategies are choosing high or low, which puts us in the top row or bottom row. Column strategies puts us in high or low, which puts us in the left column or right column. Rows payoff is first, columns payoff is second in a given cell. All right, find the Nash equilibrium. This is played just once. It's a prisoner's dilemma. So the way we find this is by looking for best responses. We consider what happens if column player plays high. Well, low player can play high and get 15, or low and get 35. They'd rather get 35, so they'll play low, so I underline 35. What if column player plays low? Well, row player could get 0 by playing high, or 10 by playing low. They'd rather get 10, so I'll underline low. What if row player plays high? What can column player do? Well, column player responding by low gets 35, responding by high gets 15, so column player will choose low, so I'll underline 35. And then what if row player selected low? Column player can react by selecting high and they get 10, or they select low and they get 10, right? Notice when you're trying to find best responses, you pay attention only to that player's own payoffs. If we play this game just once, the Nash equilibria, where we've got 2 check marks, 2 underlines, right, is going to be will be the Nash equilibria. We found this by best responses, so we know that no player can do better, conditional on already being in this cell of the game. Report and describe a strategy that will promote tacit collusion as the equilibrium if the interaction is indefinitely repeated. Right, so here I want a strategy. There's a slide in the tacit collusion lecture that gave a strategy that promotes tacit collusion, and that's the one I'm looking for. Although I also accepted the Grimm trigger strategy, because that would actually promote tacit collusion. It's a little bit less optimistic than we would need to get collusion, but so I accepted that as well. But here's one such strategy that will promote tacit collusion. Both play high until someone defects. If someone defects, then play low for a punishment phase. In this case, has to be at least 5 periods. So it was a really big error to say something like the Nash equilibria was playing high, or was just high. Sorry, the tacit collusion equilibrium was high, because that's alone just pricing high isn't enough to sustain collusion. You need the threat of pricing low to reinforce the fact that people only ever price high. Here's how we find the punishment phase of 5. So I'm summing up the payoffs to continued cooperation, pricing high, versus defecting and getting 35 immediately, but then a stream of 10s for being punished, right? So 15 plus 15 plus 15 plus 15 plus 15, right? Or 15 times 5 is what, 75? And then 35 plus 40, that's also 75. So 5 periods out, if we call this period 1, we're indifferent between defecting and not defecting. Going out the 6th period, or 5 periods of punishment, gets us to, 6 times 15 is 90, or 35 plus 50 is 85. Then the last one, does the firm ever actually employ any sort of punishment or not? Actually, no, not in equilibria. So the punishment strategy actually promotes cooperation by so successfully deterring a deviation that you never actually have to punish, is the idea, right? So the firm's actually not going to punish. They've got this threat of punishment, and they say that they would punish if they need to. However, if the punishment is credible, they won't actually need to punish. Not in equilibrium, they'll just cooperate forever, because if there's 5 periods of punishment, and we know this, then well, 6 periods into the future, I'm better off having always cooperated than having defected once, right? Okay. So here's the Stackelberg. Suppose the market for some service is given by prices 16 minus Q, requires marginal cost of 4 to offer the service. That means the same marginal cost of 4 for any firm in the market. The market's served by 2 firms. Initially, there's an incumbent, and a rival entrant begins operating after having observed the choices made by the incumbent. So that suggests sequential timing, but if that wasn't enough of a hint, and I judged it might not be, I said find the Stackelberg price, quantity, and profits. So Stackelberg is sequential. It's like Cournot, but it's Stackelberg. Cournot is officially simultaneous timing, so they're not observing each other's choices, at least not in the period that they're selecting in. Anyway, it starts off kind of the same. We find the Cournot best response function for the follower, or for player 2, then we plug that into the Stackelberg leader's profit function. Right, so here's the follower's profits. So this is going to be demand, price, 16 minus Q1 minus Q2 times Q2 minus costs. Right, this is actually total revenue right here. This is total cost right here. So I take the derivative, it's going to be MR equals MC. But anyway, it's going to be, I think what I did is, I collapsed this pretty quick. I collapsed the algebra, and then I took the derivative immediately. So this is going to be 16Q2 minus Q1 Q2 minus Q2 squared minus 4Q2. And then take the derivative, it'll be 12 minus Q1 minus 2Q2 equals 0. Solving for Q2, I get 12 minus Q1 over 2. And then remember I said, you can solve Cournot, and you can keep this as a big fraction, but it's really easy to make a mistake. And so with this division bar not multiplying through by enough 2's, so I was dividing through this first term. If it's even or nicely divisible by 2. So, what I mean by nicely divisible by 2 is maybe if this is 13, that's not so bad because this will be 6.5, which isn't horrible to look at, right? So I'd still actually probably divide this through if this was 13. Here it's 12, so it's nice. It's just 6 because that's even. It's still even. Anyway, so then it's going to be 6 minus 1/2 Q is equal to Q2. I'm going to drop this thing into my Stackelberg leader's profit function, and that's just easier to deal with because I've got this 1/2 Q rather than this big division quotient bar, right? Anyway, so now what I've got is an algebraic expression with one unknown, right? These are all Q1s, right? What justifies that is because the leader knows that the follower is going to react to the leader's choice. The leader is going to perceive the follower's selection as a function, as a strategy, as a best response function. So that's why I can do that. I'll drop this in here. That's how you solve Stackelberg. And now solving this, or distributing and then solving out before I take any derivatives, I'm just going to clean up the algebra, collect like terms. I'm going to get a 16Q1 minus 4Q1, that's 12Q1. I'm going to get a q1 squared, or sorry, a minus q1 squared from this right here. I'm going to get a minus 6q1, and then I'm going to get a plus 1/2 q1 squared. So then when this gets cleaned up, I'm going to just have a 6q1 minus a 1/2 q1 squared. Then I'll take my derivative. So really easy. I mean, the fact is, with Stackelberg, by the time you're taking your derivative, right, the thing looks way nicer than where you started from. And so here we go. I'll just take my derivative, and my Stackelberg liter quantity falls out kind of immediately. And so I don't know what I was doing here. I wrote q1 is equal to 0. I must have lost my 6. This is supposed to be q1 is equal to 6, right? Obviously, like look what we're solving here. I did that either too quick and maybe I just got distracted or whatever. This should be q1 equals 6. So maybe just like, highlight this part right here because q1 is just going to be 6. You know that though. Here's monopoly quantity is going to be 6. If you just solve the monopoly problem for this class of Stackelberg games, the Stackelberg liter is going to just produce the monopoly quantity. Anyway, so if the Stackelberg liter produces 6, the Stackelberg follower is going to react and produce 6 minus 1/2 times 6, or 6 minus 3, or 3. So Stackelberg liter is going to produce 6, Stackelberg follower is going to produce 3. There's going to be 9 units in the market. 16 minus 9 is 7, so that'll be my market price. My liter's profits are going to be 7 minus 4, that's price minus marginal cost times the 6 units, which is 18. My follower's profits are going to be 7 minus 4 times 3, which is 9. Okay, so then I said, suppose rather than allowing the entrant to come into the market and compete as Stackelberg duopolist, the incumbent decides to purchase and merge. Think about what we need to model this. What's the maximum amount the incumbent would pay to acquire the entrant? What's the minimum compensation the entrant would accept to be bought out? So you got to be a little bit clever here. I wanted you to think about the economic logic of what's going on here, right? So think about what's the max and min that they would accept to agree to this deal. I had a question just like this on the midterm 2 additional exercises, but it was in the context of Cournot. So that's not exactly what we're doing here, but it's the same sort of logic. So what I want to do is I want to determine what are going to be the profits that we have when we're playing Stackelberg. Well, our Stackelberg profits for the leader are 18, for the follower it's 9. So the follower is going to demand at least payment of 9 as the purchase price, right? Because they're going to say, why would I agree to, if I know for sure I'm going to get 9, why would I agree to sell for anything less than 9? Because I'll just be a Stackelberg follower and I'll get 9. So the follower is going to demand at least 9. Now, as a monopoly, the leader is going to get profits of 36. That was from, here's our MR equals MC. Here's solving for the monopoly quantity and monopoly price and monopoly profits, right? So the inverse demand was 16 minus Q. So marginal revenue has the same vertical intercept, but twice the slope, right? So 16 minus 2Q is equal to 4 was my marginal cost. 16 minus 4 is 12 equals 2Q. We're solving, Q is 6. We knew that from above if I had written this correctly, right? We know the Stackelberg, in this case, Stackelberg liter is going to produce the monopolies quantity. Anyway, we can find the price here. 16 minus 6 is 10. That's going to be my monopoly price. 10 minus 4 is 6 times 6 is 36 is my monopoly profits. So as a Stackelberg monopolist, as a Stackelberg firm, the leader gets profits of 18, but as a monopolist, they get 36. So they'd be willing to pay up to 18 to buy the other firm, but not more than 18. Say they paid 19, right? If they paid 19, then their profits as a monopoly would be reduced 36 minus 19 down to 17, and they wouldn't want to do that, right? So our Stackelberg leader is willing to pay somewhere between the monopoly profits and the Stackelberg leader profits, right? So 36 minus 18, this is where I got that 18 from. At minimum, right, the Stackelberg follower requires 9. The Stackelberg leader will pay no more than 18. So we know if the leader ends up buying the follower, it'll take place at a price in that interval between 9 and 18. So 9 is fine, they'd be indifferent. 18 is fine, but anything smaller and anything larger, one or the other would complain. All right, so suppose you run a shop that produces widgets. You're considering two compensation schemes. You pay your worker a weekly wage of W, or you may pay a weekly wage plus a piece rate per widget S. So here's the cost of effort function, 10,000 times E squared minus 2E plus 2. The worker's utility is going to be wage minus the cost of effort. They have an outside option, meaning if we don't hire them, they can get 80,000 if they choose not to accept your offer, right? Assume 1 unit of effort means 1 widget. You can sell 1 widget for 100,000, assuming your only cost is labor. This is the one from lecture with new numbers. I made it widgets instead of sales, right? And then I made this 80,000 instead of 50,000. And so you know, kind of without doing any work, that the effort has to be, the fixed salary effort is 1, the full incentive effort, we're going to pay them 100,000, and their effort is going to be 6, if you remember from lecture. And then you have to solve for the remaining things. If not, we'll kind of go through this a little bit more deliberately. So what I want to do is I want to say, all right, if we are not conditioning payment on our effort, what's going to be the optimal effort level for our worker? They're definitely going to shirk, but then how bad is it going to be? What's going to be the effort level they'll put in? So let's look at their utility. It's going to be W minus 10,000, I just wrote 10 there, times this nice quadratic, or minus 10 times E squared plus 20E minus 20. Taking the derivative, it's minus 20E plus 20, or solving, E is 1. And then what we can do is we can evaluate what's going to be their utility, but more usefully, it's going to be what's got to be the wage to keep them indifferent between working for us, which is going to cost them a psychological cost of $10,000, because if we evaluate this nice quadratic for 1, right, so we evaluate this at 1, it'll be 1 squared minus 2 plus 2. That comes out to just 1 times 10,000, means wage minus 10,000 is going to be their utility for working for us. If we've got to keep that equal to at least 80,000, we have to pay them 90,000. Right, so that's just this work right here. Right, if we paid them less than 90,000, the psychological penalty for putting in 1 unit of effort is too great. They won't accept the offer because they'd be better off with their outside option. We could pay them more, but we wouldn't need to. And so the optimal payment would be 90,000, and then our profits are going to be the 100,000 for the 1 widget they'll make minus the 90,000 we paid, which is 10,000. All right, suppose we pay the full incentive contract. So we're going to give them the full returns of their efforts. So each additional widget they made earned us 100,000. We'll just give that right back to it'd be like a full commission. We'll give that to the worker. So now this is going to be A plus 100,000 E minus 10,000 times this nice quadratic. So we can find the effort level. It would be 20,000 E plus 20,000 equals 0. And then this is after I've taken the derivative. Or let's see, 120,000 minus 20,000. And so then it's 120,000 divided by 20,000, because this was an E equals E, which is 6. So that's where that came from. Or you could follow, I mean, that was from the notes as well. Right, so then we have to find what's going to be the effort, or what's going to be the wage, the fixed portion, to keep them indifferent, so they get exactly 80,000 either way. Right, so it's going to be A plus 100,000 times 6, because they're going to make 6 widgets. They're going to get 100,000 for each widget, so they're going to get 600,000. Then their psychic effort cost is going to be 10,000 times, we got to evaluate this nice quadratic at 6. So it's going to be 36 minus 12 plus 2. So 36 minus 12 plus 2 brings us to 26. Times 10,000 gets us, minus 260,000. 600,000 minus that stuff is 340,000. We need this to be equal to 80,000. So A has to be actually negative 260,000. I made A positive. I forgot the negative here, right? So I think the way that I did this, what I was thinking of, I was calculating out just the magnitude or whatever. This is negative because this will be 340,000 minus 260,000 gives them 80,000, and leaves them with 80,000. They'll be indifferent between working and not. So this then becomes our per unit profits. Maybe that's why I left this as 260,000. 260,000 was our per unit profits. In grading, I didn't pay a whole lot of attention to the sign. So I was looking for, I was looking for the right values, and then because there's maybe, I mean, I don't know. So maybe you did exactly what I did here, right? All right. So why did they pay us $260,000? How's that work? Well, remember from lecture we were saying this would be something like you're paying somebody to sit at a kiosk in the mall, or a salesperson to be at the car lot, right? And they're there 40 hours a week, right? They're there all the time, putting in, like, giving us a lot of value. We can have this physical brick and mortar location because the workers there. They're giving us this value. Without the workers being there, we wouldn't be able to have that thing. And so that's where this 260,000, one of the places we could talk about that coming in. It's not literally the workers writing us a check for $260,000. No, it's that they're giving us this value, right? And then we're giving them 100,000 back for everything they sell, of which it'll be, in total 600,000. Anyway, so I'll go ahead and conclude here. Hope you enjoyed the video, and see you next time.